All right, guys. So our eighth unit of 2014 is also this is the last unit. Is this unit 9? Have I got this mislabeled? All right, unit 9, gases. Unit 8. Hang on here. We'll do some math. Unit 8 plus 1 equals 9 is gases. How's that? All right. Okay. It happens to be chapter 10 in your book, so if you're interested in looking in your book, we're 10.1 right now, characteristics of gases. Here's a summary of what chapter 10.1 in your book says. Dr. Zumdahl says gases are highly compressible. Okay. That's basically because there's so much space in between gas particles, in between molecules, that you can push them together closer much, much easier than you can with liquids and solids. Gases tend to expand to fill their container. What that means is that the top of the container and the bottom of the container would contain equal densities of a gas, as long as your container isn't significantly large. If your container is the size of the Sears Tower, then we're going to have difficulty with that definition there. Okay. Otherwise, most containers, gases are going to expand to fill it perfectly fine. All right. They're going to mix evenly and completely when confined to the same container. What that means is if somebody opens up a little container of perfume, that means that initially, right at that point where it got opened, you're going to have a large amount of smell, right? But if you wait a few minutes, that smell will diffuse out into the entire room. It'll fill it completely. I could have used an example using chili, couldn't I? Different kind of smell. You guys are way too busy writing this stuff to laugh at that joke. All right. Molecules are relatively far apart, is stated in the fourth bullet down there, which is something I talked about in the first bullet. They're highly compressible, so the molecules are very far apart. And that relatively refers to compared to the size of the molecules. Compared to size of molecules. Gases have much lower densities. Again, that's because of all that space that's in there. And then finally, they exert pressure and are in constant motion. Once we got the facts down, we got to talk about the KMT, known as the kinetic molecular theory. Okay, we'll get this done in 2 slides also, relatively quick. Okay, but there's a bit of reading to do in that packet about it. Okay. Gas molecules are separated from each other by great distances. We just said that, right? Okay, so these are assumptions of the kinetic molecular theory. The molecules take up very little volume, and the space between them takes up a lot of volume. I think we just really hit home on that, right? Gas molecules are in constant, random, elastic motion, and energy is transferred in a collision but conserved in the entire system. So that's what elastic means. Elastic basically means that when a gas molecule runs into another gas molecule, let's say one gas molecule standing still, just for the sake of argument. The other one runs into it at 100 miles an hour. How fast does that second gas molecule collide off if it's elastic? Elastic means that momentum is conserved. So it means that it's going to fly off at 100 miles an hour. Now, getting a gas molecule to not move is hard because they all have temperature, they all have energy, so they're all going to be constantly moving. Another assumption of the kinetic molecular theory is that gas molecules do not exert any attractive or repulsive forces on each other. That means that when they fly past each other, they're not going to attract and they're not going to repel each other. It assumes they're completely and totally neutral. Now, from our standpoint, we might believe that for a moment, right? So here's a couple things that I just talked about with you guys, but weren't actually on that slide. Kinetic energy is proportional to the temperature of the gas. Kinetic energy is energy of motion. Okay, so how fast they're moving, how fast they're vibrating, has to do with their temperature. The temperature is a measure of motion. The higher the temperature, the faster the particles move. So if you heat up a gas, you're going to see that the atoms and the molecules within it are moving faster. If you cool it down, the atoms and the molecules will slow down and move slower. And then the second thing that's stated here is gas pressure is a result of collision between molecules and the wall of a container. So in other words, the pressure that a gas exerts is going to be due to the fact that these molecules inside of the container are slamming into the walls of the container. The more that we need to talk about here is about pressure. Okay, and I'm going to get that song stuck in my head now. The little bit of pressure that we need to talk about here is that pressure is the amount of force applied over an area. Okay. Atmospheric pressure is the weight of the air per unit of area. And you can see from that picture there, you can start thinking about it for a second. We are under an enormous amount of pressure right now. Did you guys wake up with a headache? Okay, because think about it this way for a second. All of the air that's stacked up in the atmosphere above us is actually pushing down on us. Think about how much that must weigh. Okay, it winds up weighing exactly 1 atmosphere if we live at sea level. We don't live at sea level, so do we have exactly 1 atmosphere on us? No. So the people in New York have more pressure on them than we have on us in Chicago. You know who's really feeling less pressure? The people that live in the Mile High City, Denver, Colorado. Death Valley, Nevada is really low, if I remember right. It's actually below sea level. Okay, so they're feeling even more pressure than the rest of us because they have a little bit extra air on top of them. Okay. Okay. So I think you guys are getting that idea that less gas particles equals less pressure. More gas particles equals more pressure. You don't have to write this information down, but if you were the kind of person that was asking, hey, how much air is up there? At sea level, you got 1 atmosphere. 4 miles up, you're about half an atmosphere. And 10 miles up, you're about 2/10 of an atmosphere of pressure. Okay, so Mile High City, you're somewhere around 1 and 5 atmospheres, probably closer to like 0.8 or 0.9. I guess that would be something interesting to look up someday, huh? I've never looked that one up. Oh, let's talk about standard pressure real quick. Normal atmospheric pressure, the pressure that you feel at sea level on a perfectly calm day, is supposed to be 1.00 atmospheres. Okay, the definition of standard pressure. But pressure is measured in several different units. Meteorologists, the people that tell you, on the news whether it's going to rain or snow tomorrow, they measure in millimeters of mercury, which is also known as torr. Okay, because that's what a barometer measures at, millimeters of mercury. So the 760 millimeters of mercury is the same thing as 1 atmosphere. Okay. Kilopascals is used by scientists quite often. 101.325 kilopascals is the same thing as 760 millimeters of mercury, which is the same thing as 1 atmosphere. So these things are all standard pressures. Okay, and we in America think we're so great, so we have our own pressure units, pounds per square inch. Okay, because we be special. Okay. So right now, you guys are feeling a pressure in the classroom of about 14.7 psi. If we're at 1 atmosphere today. Okay. So if you want to feel under a lot of pressure, think about this. A postage stamp is about a square inch, right? It's about 1 inch by 1 inch, give or take. Okay. It depends on the stamp. But give or take, just think about a postage stamp for a second. Now imagine for a moment, use your imagination, how many postage stamps would it take to wrap around my head? Okay. More than 28. Not just around my head in a line, but think about every square inch of my head. Or yours. Okay, so, 375 is the number I heard shouted out, right? 375 pounds per square inch. So that means my head right now, if I've got 375 square inches on my head, and some people say I've got a big head, but, all right, 375 times 14.7, that gives me 5,512 pounds of pressure being exerted by the atmosphere alone on my head. Right, I multiplied it by 14.7. Okay. Now, if you got a smaller head, you're not using 375 postage stamps, right? Maybe 100. Well, no, 100 is too small. For the lecture, Kelvin temperature scale. I think we've talked about this one before, right? Okay. If we haven't, here's the idea. The Kelvin temperature scale is a different temperature scale. It's measured on an absolute zero system, such that the idea is that if a gas gets down to 0 Kelvin, the lowest possible temperature, absolute zero, that there's not going to be any vibration left. There's not going to be any movement of molecules left. So Kelvin was the guy who decided, hey, we can't, what does no movement look like? Right? We know what no movement looks like. What does negative movement look like? There's no such thing, right? All right, so yeah, brain explosion. So the Kelvin temperature system basically has this idea that there's an absolute lowest temperature, and that theoretically you can't get any lower. So far, there have been some experiments that initially said, hey, Kelvin was wrong. Matter of fact, one of them was last summer, and one of them that I know about was the summer before that. It turns out that those experiments didn't, they weren't doing the right stuff. They were making some assumptions that weren't true. So it turned out that they actually supported Kelvin's theory after the assumptions were found. Doing a conversion, I will go back in just a second. Doing a conversion is real easy. Kelvin is the Celsius temperature plus 273.15. So the freezing point of water is 0 degrees Celsius because science. That's fine.